And so we're going to do spherical and cylindrical pressure vessels. So we're talking about an empty, a hollow shape with gas or liquid on the inside with a pressure. And I'm going to start out with spherical. And then I'm going to do cylindrical, which you can also think of as pipes. All right, so the first one I'm going to do is a spherical. And for these to give good results, the walls have to be fairly thin. That's usually the case in something that's built to withstand pressure anyways. But if you have really thick walls, these calculations won't be good. So for a spherical pressure vessel, we're talking about a shape like this that has a pressure on the inside pushing out, and a pressure on the outside pushing in. Call that P out. And so I'm going to base this calculation on the total pressure. We're going to assume that that the inside pressure is higher than the outside pressure. If the outside pressure is higher, then you have to think about, even though it's linear and our calculations are accurate in a way, you have to worry about buckling of the surface if the outer pressure is higher. So I'm going to call the total pressure P in minus P out. We're going to assume that's positive. And I'm going to think about the cross section. So imagine you take a slice of this thing. Okay. This is supposed to be 1/2 of the sphere. Okay, so what loads are acting on this? Well, there's the pressure P that's pushing from the half that's missing onto the half that we're including. Okay. And if we think of this as a free body diagram, I'm not going to write that as a pressure, I'm going to write it as a force. But the way you calculate that force is it's the pressure times the area. Okay. We took a slice including the gas or the liquid that's in this half. It's flat, yes, that's right. It's a flat surface there. And so that's one of the forces, and then the other force is the metal that I'm not including in this body pulling on the, or I say metal, it doesn't have to be metal, but the material that we excluded pulling on the material that we included. Okay. So I'll call that F for now. And we're going to assume that that force F is just all, so that we're going to assume that the stress around the edge is all normal stress. It's just pulling. It's all in tension. Okay. And so that force F is going to be equal to the normal stress, I'll call it sigma, times the area of that rim. Okay, so anybody have an idea how we're going to calculate the area of that rim? This is actually a trick that comes up a lot of times in derivations. Thickness of T. Think of, so this area is like a long circular strip, and we're just going to imagine breaking the connection of that strip, straightening it out, and then it's a long, skinny rectangle, you know, with a width that's equal to T. And so the area is the perimeter, 2 pi r. Yeah, well, it's thin enough that we'll assume it's the same. They're about the same. And so this is the area of the exposed material. Okay, are you with me on that? And now the area A that I have in red up here that we're multiplying by the pressure is equal to pi r squared, right? With me on that? And now we can use Newton's second law to say that stress times 2 pi r times the thickness that's going, let's call that positive, and then minus the stress going the other way, or the force going the other way, which is the pressure times pi r squared is equal to 0. You can divide everything by pi, divide everything by r. And now solve for the stress, and you get that the stress is equal to the pressure times r over 2t. Okay, so that's a tensile. And now we have to think about the direction of this tensile stress. Well, a sphere obviously has every kind of symmetry. And so it turns out that no matter how you orient your coordinate system, as long as two of your axes are in the plane of a point on there, that's going to be the tensile stress, say along x. You could move your x any way you want. And so because of symmetry, if the x and y axes are tangent to the surface at the desired point, then the stress tensor is PR over 2t for x, PR over 2t for y, and 0 for z. Okay, so if you have a sphere and the point that you're interested in is here, put your x-axis tangent to that point, your y-axis tangent to that point, your z-axis out of the page, out of the, normal to the surface, and this is your stress tensor. What would you get if you calculated the principal stress for a point on this surface? This is a trick question. It's the same. That is a principal stress because there's no shears. And so that means that P max is the maximum of these minus the minimum. So PR over 2T minus 0 divided by 2. And so the maximum shear stress is PR over 4T. Let me do an example. Let's say that we have a spherical pressure vessel that's filled with water at a depth of, at an ocean depth of 1,000 meters. And now that it's full and sealed, we start to bring it up toward the surface. If it's brought toward the surface, at what depth would the tensile stress value, let's say the maximum principal stress, or the maximum normal stress, be 1 times 10 to the 7 pascals. We need a size for this thing, so let's say that the radius is 0.3 meters, and let's say that the thickness is 1 millimeter. Okay, I think the application of this question is pretty obvious. Not really. I can't think of any reason you would ever do this, but still, it's like kind of a cool question. Okay, so you fill this thing with water down low in the ocean. The pressure inside stays the same, and as you get closer and closer to the surface, the outer pressure gets lower and lower. Okay. At what point is the difference in pressure going to be enough to get this pretty significant stress in the walls, where you'd start to worry about damage happening to the walls of this container? Okay. By the way, 1 millimeter is still pretty thick for, think about like an old 70s bicycle, like a old 10-speed, the heavy steel bicycle. You have any feel for how thick? So all the tubes are, steel tubes that are hollow in the middle. Okay. They feel like there's a pretty significant amount of steel there. Those tubes are actually, the tube thickness is less than 1 millimeter. So we're talking about as far as engineered pressure vessels, whatever go, this is a pretty thick container. All right, well, let's do this. I mean, maybe we'll get to the surface and it still won't be that high. I'm not sure, but we'll see. So the pressure, anybody remember how to calculate the pressure at a given depth? Yeah, right. So the pressure is rho, the density of the liquid, times the acceleration of gravity times, h, but we're talking about the depth. And so if this is water, let's ignore the fact that it's salt water. I don't know how that changes this a little bit. But the density of water is about 1,000 kilograms per cubic meter. The acceleration of gravity is 9.81 meters per second squared. Since this is all in SI units, we're talking about a depth of 5,000. 1,000 meters, yeah. So that's, this is meters. 9.81 times 10 to the 6, and this is a pressure, so this is pascals, SI units of pressure. That's a lot of pressure. But so if we take this empty pressure vessel down there and fill it at that pressure, then down at 1,000 meters of depth, it has that same high pressure pushing out that it does pushing in. And so how are we going to do this? Well, let's think, let's first figure out the pressure difference that would be required to come up with that stress, okay? And then we'll calculate how much change in depth you need for that change in pressure, okay? Everyone with me on that? So to get a stress of 1 times 10 to the 7th pascals, we need our P times the radius of this thing. What did I say, 0.3? Divided by 2 times the thickness. To be equal to 1 times 10 to the 7th. And so the pressure, and remember this pressure P in the equation is the difference in pressure from the inside to the outside. So this has to be equal to 1 times 10 to the 7 times 2 times 0.001 divided by 0.3. And so you get 6.6 repeating times 10 to the 5th, I believe. Okay, so that's our P. But that's a pressure difference. So this P has to be equal to the inner pressure that we already figured out. So this is P inner minus P outer. So that's 9.81 times 10 to the 6th minus P outer. And so P outer has to be equal to, let's see, what am I doing here? P outer is 9.81 times 10 to the 6th minus 6.6 repeating times 10 to the 4th. What is that, 9.74 or something? Times 10 to the 6th. And now we just have to figure out at what depth we have this pressure. This is still a gigantic pressure. So rho GH is 1,000 times 9.81 times H is equal to 9.74 times 10 to the 6th. So H is equal to 9.74 times 10 to the 6th divided by 1,000 times 9.81. And what do you get for that depth? 993. Okay, let's calculate what the stress is at the surface. So what's that tensile stress? At the surface? Well, we didn't take atmospheric pressure into account when we calculated that fluid pressure. So in essence, what we did was we calculated the gauge pressure, the pressure in addition to atmospheric pressure, which means that the pressure at the surface of the water is going to be 0. Okay. So we're doing this with gauge pressure, pressure compared to 1 atmosphere. So at the surface, P outer is 0. Okay, so at the surface, P is equal to P inner minus P outer. And so that's 9.81 times 10 to the 6th. The tensile stress is this pressure difference P times R over 2T. And so that's 9.81 times 10 to the 6th times the radius of the sphere divided by 2 millimeters. 1.4715 times 10 to the 9 pascals. Well, steel can't withstand that amount of stress, so this thing will explode. So the other common pressure vessel shape is cylindrical. So we're talking about if we're looking at a point like this, we're going to use a coordinate system again that has the x-axis in that's so imagine a tangent plane at that point. The x-axis is in that plane, the y-axis is in that plane, and the z-axis is out. Well, we don't have all the same symmetry here that we had in the cylinder, and so we're still only going to have tensile stresses in the x and y directions, but they're going to be different values than each other, okay? So this time, the XX normal stress is not going to be the same as the YY normal stress, but we're still going to have the Z normal stress 0, and we're still not going to have any shears. So first, let's think about the stress. So let's do the Y stress first. And we're not going to include the ends. This is the thickness of the walls. We're still going to think about a radius r, and we're also going to think about a length L. Okay, so what forces do you have here? Well, you have the pressure of the part that we excluded pushing down on the fluid that we included. And then we have the tension of the material that we excluded pulling on the material we included. Okay. The red, the pressure of the fluid pushing on the fluid that we included here is P times A, and that A is going to be different than it was before. And the force that the excluded material applies to the included material, I'm going to call F, and we'll calculate that. Those two are going to have to be equal to each other, again, for this to be an equilibrium. Okay, so F is equal to the stress times the total material area. And so let's calculate that material area. We have, you can think of this as made up of two different rectangles. Each one of those rectangles has a thickness of P and a length of L. All right, so what's the area? One of those rectangles is LT, two of them is 2LT. And now we have to calculate the area of the exposed area of fluid. So what's that area going to be? Well, it has, so this A, you can think of it as a length times a width. The length is L. The width is 2 of those radii. So 2LR. And now Newton's second law says the stress times 2L, this is a lowercase t, 2LT minus the pressure times 2LR is equal to 0. And we can make some cancellations, the 2's and the L's. And you get that the YY normal stress is equal to PR over T, 1T. This is called the hoop stress. Everybody with me on that one? Okay, so that's the tensile stress in this y direction. Now we have to figure out the tensile stress, like, you know, this pressure could open it up like a smoker, yep. But it could also blow it apart like this. So now we have to calculate the stress, the tensile stress in the x direction. So I'll do a free body diagram. Like this. And again, there's a force applied to the included fluid by the excluded fluid, like that. And the magnitude of that force is the pressure times the area. And then resisting that is the pressure applied to the included, you know, the tension applied to the included material by the excluded material. And I'll call that F. To calculate F, I'm going to do it the same way I did with the sphere. So we have, so if you think of taking that that big narrow ring and breaking 2 ends of it and stretching it out into a long skinny rectangle, you have the circumference, so 2 pi r, times the thickness, that's the area, and then we're multiplying that by the stress. The area of the fluid that's exposed, A, is pi r squared. And so now we can go to Newton's second law again. And we get that sigma times 2 pi RT minus pressure times pi r squared is equal to 0. Some cancellations, pi goes away, one of the r's goes away, and we get the same thing that we got for the stress for the spherical shape. So sigma xx is equal to PR over 2t. And so the stress tensor is in the x position PR over 2t. In the y position PR over t. And 0 in the z direction. And so in the case of a cylindrical pressure vessel, the maximum shear stress is the bigger of these two stresses, which is PR over T, minus the minimum. It's all tension, so it's 0, divided by 2. And so the maximum shear stress is PR over 2T.